Hello everyone, welcome back to the Everyday channel. Computers today are incredibly advanced, with developments like augmented reality, virtual reality, and much more. But what if there was a computer even more powerful than today's supercomputers? Could it exist? The answer is yes, and it's called a quantum computer. Let's dive into a brief overview of what quantum computing is. Let's go. First, let's understand what quantum means. You've probably heard terms like quantum physics or quantum leap. Does quantum make you think of something enormous or impossible? Actually, quantum refers to the smallest possible unit of something. You can't break it down any further. So, what is a quantum computer? Is it the smallest part of a computer? No, not at all. Quantum computers refers to quantum computing, which is based on the principles of quantum mechanics, not the size of the computer. A quantum computer uses phenomena like superposition, interference, and entanglement to perform calculations. These machines are extremely powerful, able to solve problems faster and more accurately than even the best supercomputers. While there's no single inventor of quantum computers, the basic idea emerged from scientific thought long ago. For instance, in the 1980s, Richard Feynman proposed the idea of quantum computers as a solution to the difficulty of simulating quantum phenomena on classical computers. He realized that to accurately simulate quantum systems, we would need a computer that operates according to the rules of quantum mechanics. Okay. I know this might sound complex, but stick with me. We'll make sense of it together. In quantum computing, there are bits and qubits. So, what are these? In classical computers, bits are like switches that represent either a 0 or a 1, or on or off. In quantum computers, qubits are similar but can exist in superposition, meaning they can be both 0 and 1 at the same time. Confusing? Yes. It's a bit mind-boggling. This is based on the quantum mechanics principle called superposition, where quantum objects like qubits can exist in multiple states simultaneously. Still confused? Okay. Let's use Schrödinger's famous thought experiment to explain. Imagine putting a cat inside a sealed box, along with a radioactive substance, a Geiger counter, and a poison bottle. If the radioactive substance decays, it triggers the Geiger counter and releases the poison. According to quantum mechanics, until you open the box, the cat is both alive and dead at the same time. That's superposition in action. Fantastic, right? But it doesn't stop there. Quantum computers also involve entanglement. What was that? Okay, entanglement occurs when two or more quantum objects become so interconnected that the state one of instantaneously affects the state of the other, no matter how far apart they are. This concept challenges classical physics. Here's a simple analogy. Imagine you're on a road trip and stop to buy street food. 2 bags of tofu, one spicy and one not. You don't know which is which. Once you open the bag and find it's spicy, you instantly know the other bag is not spicy. That's entanglement. So in real quantum mechanics, it's much more complex. Got it? If not, don't worry. You can find plenty of resources online to explore further. I'm trying to keep this as simple as possible. Now, how do quantum computers compare to classical computers? Here I've got an image to illustrate the difference. Let me explain briefly. The image shows the vast differences between classical computers and quantum computers. Classical computers can only represent 2 data points at the same time, while quantum computers can handle far more. Let's break it down. Data processing. Classical computing uses logic gates that manipulate bits based on Boolean logic, 0 or 1. But quantum computing uses quantum gates, allowing to perform more complex operations like entanglement and superposition. Quantum computers can solve certain problems, like factoring large numbers or searching database, far more efficiently because qubits and evaluate many possibilities simultaneously. Classical computers provide deterministic results, meaning the same input always gives the same output. Quantum computers, on the other hand, provide probabilistic results, meaning the outcome can vary and multiple tests may be needed to get the desired result. But don't worry, you won't need a quantum computer to diagnose your illness anytime soon. Or you might be told you only have 2 weeks to live. Although quantum computing might seem daunting, it's already being used in areas like biological calculations, biochemistry, and more. As Feynman said in his 1982 journal, Nature is not classical. If you want to simulate nature, you'd better make it quantum mechanical. It's complex, but it's essential for understanding things that classical computers can't simulate, such as enzyme reaction or brain function. Quantum mechanics is also being explored in areas like photosynthesis, neural signal processing, and protein-drug interactions. To sum it all up, quantum mechanics deals with the smallest building blocks of the universe, where concepts like superposition and entanglement describe the unique behaviors of quantum objects. Quantum computers leverage this principle to perform calculations at speeds and accuracy far beyond what classical computers can achieve. While it may seem confusing, quantum computing is already being applied in various fields, showing just how revolutionary it can be. Alright guys, that's it for today's topic. Feeling confused? You're not alone. Quantum computing is not an easy subject, but I hope I've managed to make it a little clearer. If you enjoyed this video, don't forget to like, comment, and share it with your friends, okay? See you on next videos. Bye.